All right, let's dive into one of those classic, brain-bending problems from Irodov's famous physics book. We're going to tackle problem 1.10. Now, when you first read it, it seems pretty tough, but you're about to see how the whole thing cracks wide open with just a simple shift in perspective. It's going to be fun.
Okay, so here's the setup. You've got two objects. They're launched at the exact same moment, from the exact same spot, and with the exact same initial speed. The only difference? Their direction. One goes straight up, the other goes out at a 60-degree angle. And our job is to figure out exactly how far apart they are after 1.7 seconds.
You know, when you first think about this, it feels like a real mess. You've got one object going straight up, slowing down, and then falling back. Meanwhile, the other one is tracing this big, sweeping curve, a parabola, across the sky. Trying to track both of those paths separately sounds like it's going to involve a whole bunch of nasty coordinate geometry and calculations.
So before we even try to solve this, we got to talk about the main tool in our toolkit. It's the one fundamental equation that governs all this kind of motion, and it's right there in the book's chapter summary.
And here it is. This one little equation, believe it or not, describes the entire path of any projectile, as long as we're ignoring air resistance. It tells us that the position, r, at any time t, depends only on two things: its initial velocity, v0, and the constant downward pull of gravity, g. That's it.
Okay, so let's try to solve this the hard way first. You know, from the perspective of someone just standing on the ground watching this whole thing happen. This is the path that seems most obvious, but it's also the most complicated.
So you could write out the position equation for body 1 and then another one for body 2. To find the distance between them, you'd have to plug 1.7 seconds into both equations, figure out their exact coordinates in space, and then use the distance formula between those 2 points. I mean, you could do it this way, but wow, it would be a slog. Super messy.
But here's the thing. There's a much smarter way to do this. A more, well, elegant way. And honestly, this is where physics gets really, really cool. By changing how we look at the problem, all that complexity just melts away.
So let's just stop for a second and ask a totally different question. Forget about watching from the ground. What if we were, say, riding on body 1, the one going straight up, and we looked over at body 2? What would its motion look like from our point of view? This is the absolute key. You see, what we're really trying to find, the distance between them, is just the length of a vector that points from one body to the other. We call this the relative position vector, delta r. And to find it, all you have to do is subtract the position vector of body 1 from the position vector of body 2.
Okay, so here's where it gets good. What happens if we plug our big motion equations from before into this simple little formula? We take the whole expression for r2 and subtract the whole expression for r1. Just watch what happens next.
And boom! There it is. This is the magic trick. That whole term with gravity in it, the 1/2 gt squared part, it's on both sides of the subtraction, so it just vanishes. It's gone. The crazy thing this tells us is that from the perspective of one body, the other one moves as if gravity doesn't even exist. It's just moving in a perfectly straight line at a constant speed.
So that changes everything. Our super complicated problem about two different parabolas has just turned into a simple distance equals speed times time problem. All the really tricky physics is done. Now it's just a bit of math.
So our game plan is super simple now. First, we'll write down the initial velocity vectors for each body. Second, we'll subtract them to find that constant relative velocity. And third, we'll find the length of that new vector and just multiply it by the time. That's it.
Okay, let's just quickly define our directions. We'll say the I vector points horizontally and the J vector points straight up. So the velocity for body 1 is easy. It's just the initial speed, v0, in the J direction. For body 2, we have to break its velocity into horizontal and vertical parts using some basic trick.
Now we just subtract them. We take the vector for body 2 and subtract the vector for body 1. The horizontal, or I part, doesn't change at all because body 1 had no horizontal velocity. And for the vertical, or J part, we just subtract v0 from the v0 sine 60 term. This new vector we're left with, delta v, represents that constant relative velocity.
All right, to find out how fast they're moving apart, which is just a speed, we need the length or magnitude of this relative velocity vector. And for that, we just use a bit of Pythagoras. We square the I component, square the J component, add them up, and take the square root. And after a little bit of algebra magic, and using that old cos squared plus sine squared equals 1 trick, it all collapses down into this really nice simple formula.
All right, we are on the home stretch. We just take the numbers the problem gave us from the very beginning, 25 meters per second for the speed, 60 degrees for the angle, and 1.7 seconds for time, and we plug them right into the formula we just found.
We run the numbers and there's our answer, 22 meters. That's it. A nice, clean number for a problem that looked anything but. And of course, it's the exact same answer you'll find in the back of our Irodov's book.
So look, the big idea here is so much bigger than just this one problem. It's a fundamental lesson about problem solving in physics. The hardest part wasn't the math, it was finding the right way to look at the situation. The moment we jumped into a different frame of reference, a hard problem became an easy one. So next time you're stuck on a problem that looks impossible, just stop and ask yourself, is there another way to look at this? Can I change my point of view?